CV2.split is used to divide the image based on the number of channels present in it. In Python, especially in OpenCV, the format in which the images are stored is in BGR. So we use the corresponding variables BGR to store the respective channels value. And again, we use image.cv2.merge for merging them back to the original image. Let's try running this and see the image. So the image one over here is Lionel Messi's image. And this is the first example. You guys have any doubt in this? If not, we'll move to the next code. So the second code is based on region of interest. Let me explain you what is region of interest. So in image processing, region of interest is the portion of image that we want to operate or filter, or we want to make some changes. For example, in this image, let's say we want to modify this part of the image, the face or the hand or the ball. So that particular point will store that particular image pixels in a separate array, and we'll try modifying it. In this case, in our example, we'll try to extract the ball from this image and in this way, and we'll try to paste it in some other region such that there are two balls in the final image. So we'll see an example based on it. So the coordinates of ball is from 280 to 340 and 330 to 390. Let me explain what that means. So that ball over here is from 280 to 330 pixels over here, and and 330 to 390. So it's from 280 over here. This the coordinate over here is 280, and here it is 280 to 280 340. So it's 280 here, 340 here, and 330 here, and 360 here. We'll try to extract this part of the image. So again, we'll read the same image in cv2.im read, and here we'll create a new variable called ball, and we will correctly copy that element, that only the ball part of the image, to ball, and we'll store it. So we saw the y coordinate is 280 to 340, and the x coordinate is from 330 to 390. We'll make such array such that it will contain all the pixel values and it will store in ball. So we'll try printing the ball image first. So this is the image of ball. Okay, so this is the image of ball. Now, what we'll do is, in this coordinates 273 to 333 and 100 to 160, we'll try overwriting the image. I'll just tell you what that means. So from 273, from this point, this coordinate is 273 and 100 to 160. We'll try pasting the ball over here, such that what we'll do is we'll copy this pixel values of the ball, and we'll overwrite at the corresponding pixels, such that such that the area over here, the pixel areas over here, will be overwritten by the ball's value. So if we do that, we are doing that by image from 273 to 333 as and 100 to 160, and we are assigning it to the ball's value. And now if we try printing it, then we'll get a new image which has two balls. So this is the image with two balls. If you guys have any doubt in this, you can ask me. Okay, I'm assuming there are no doubts. Let's go to the next example. So in the next example, I'll be demonstrating how to add an image. So the image which I'll be using over here is image 2. Let me show you the image. So this is the image 2 which I'm going to use. So yeah, so I'm just assigning that to variable image 2. These all parts you guys are familiar with. Now what I'll be doing is I'll be first explaining what an add function is. We'll be using an add function to add the two images. So yeah. So this is the add function. Add function accepts these parameters. The first parameter is the source parameter. The second is the second source. So we'll be adding source 1 and source 2. Output array is destination. Mask, we are not caring about mask and data type now. We are leaving them default, and we will also not be using the output array because the function cv2.add, however, returns the sum of it. So we'll not be caring about the output array also. So what add function does is it will do the elementary function it will add element wise corresponding values of each image. So let's say this image and this image, for both the images the corresponding pixel values are added. Let's say the black part over here is 0 and the white part over here is 255. So these pixel values are added and the resultant sum is stored in the final output. And for that we need to have both the image sizes to be same, but here in this case it is not same, so we will have to change that again. So I'm writing image is equal to cv2.resize. So we are using a resize function here. Resize function is used to resize the image and to a corresponding array dimensions. So the first parameter is the source, which is image itself, and the second parameter is the pixel dimensions. I mean the array dimensions, which I'm assuming it to be 5 and 2. 5 and 2. These are some random values which I've taken, and for the images to be for the addition to be possible, both the images must be of the same size. So I'm assigning image 2 also to the same size, cv2.resize image 2 is the same dimensions, 512 and 512. Now we'll try combining them. If we combine them using add function, we'll get the sum of image 1 and image 2. So this is the final image. So this white portion of the image is having all pixel values into this white portion is completely white is represented by RGB 255. All the three channels are 255. So that is the maximum possible uh, brightness of the particular pixel value. That's why in our final image we are having all the portions white and only the black portions is covered by the image part, that is the image 1 part. But now if we suppose we don't want to do the same, if we want to add in ratios, then we'll have to use another function called add using add weighted. So let me explain you what add weighted function is. So this is the add weighted function. What add weighted function is, it accepts so it works based on this principle. So this is the final array value, that is the sum of source 1 into alpha plus source 2 into beta plus gamma. So the function add weighted accepts all the parameters source 1, alpha, source 2, beta and gamma. So this is the add weighted function, and we'll be seeing it in the next example. So in the next example, we are doing combined is equal to cv2.add weighted image we are taking alpha value as 0.7, beta value as 0.3, and the gamma value as 0 because we have no use of it. And if we now try to print this image, we'll see that 70% is 70% of the image is from image 1 and 30% is from image 2. Since 0.7 plus 0.3 is 1, so we'll have 70% in image 1 and 30% in image 2. So we can see that there is 70% of image 1 and 30% of image 2. Now, if we try comparing this part and this part of the image, we'll see that these two are exactly the same because black color in image 2 was having all RGB channels 0. So this portion and this portion of the images will be only 70% of it, and the rest all will be a sum of both the images in corresponding weights. Now let's see bitwise operations on images. Before that, you guys need to be familiar with basic operation on bits. So these are the basic operations which can be performed on bits. One is AND, OR, and XOR operation. So let me just make you guys recall that AND operation is the product of both the bits A and B. So if it is 0, 0, if all the outputs are high, then the output of the AND operation will be high. If any of the output is 0, then the operation of it will be low. Similarly, in logical OR, if both the values are low, only then the output will be low. Otherwise, the output will always be high. In XOR operation, what happens is if both A, B are same, then output will be 0. If A, B are different, then output will be 1. Or otherwise, you can say that if there are even number of ones, the output will be 0. And if there are odd number of ones, the output will be 1. So let me explain you this code. I'll also be demonstrating this. I'll be demonstrating pixel by pixel bitwise operations. For that, I'll first define these images. So image 1 is equal to np.zeros. So np.zeros is a function which is used to calculate, which is used to make an array of size. I'm mentioning the size here. It is 250, 503. So there are three number of channels RGB and np.unit8. Unit8 is nothing but there are 8 bits accepted by this array, and each bit will have 8 bits, and that so 8 bits in the sense 2 power 8. So it will be 256 values. That is from 0 to 255. So I'm defining a function like that, np.zeros with this dimensions and this data type. So I'll get what I'll get from this portion of the image is nothing but a dark black image with dimensions 250, 500. Let's just check how it looks. I'll comment this portion of image also. And now if I try running the image, I'll get a dark image. So I'm getting a dark image with 250, 503 as its dimensions. Now, from the previous session, you guys might be familiar with the rectangle, how this rectangle function works. So your image 1 is equal to cv2.rectangle. It adds a rectangle in the image with starting coordinate 200, 0 and the second coordinate 300, 100. Let me make you clear of it. So it accepts coordinate over here and here. So this coordinate is 0, 0 and this coordinate is 250, 250. So it's 300, 100. So 200 to 0 and 300 to 100, and I'm assigning those values RGB as 255, 255, 255. So all the channels RGB are high, so the corresponding image will also be high. Now if I try running the code for this, I'll see that from 200, 0, and from these two coordinates, I have created a rectangle which is having RGB 255, so it has white image over it. Now let's see how the second image looks. I'm using for a second image np.full. np.full is a function which is used to create a array of this dimension. So whatever the dimension of array is, that is the image which is created, and I'm assigning all the values high, which is 255. So it is a white image, and its data type is np.uint8. I already explained what uint8 is, and now for that image, I'm passing the image again, and I'm drawing a rectangle from coordinate 0, 0 to 250, 250 with all the RGB as low, so it'll be black, and -1 represents that it'll be a solid image. So now if I try printing cv2.image show, you'll see that this is the first image. So this is the second image. Earlier I had created a black image with a white image with all the pixel values high, but now what I did was I wrote a rectangle over it, which is completely solid black from 0, 0 to 250, 250. So until this part, is there any doubts? So if there is no doubts, I'll go to the next part. So now I'll be performing the bitwise operations on each image. So the first operation is bit and. For that, I'll be using cv2.bitwise and. What bitwise and does is for each pixel values, it does an AND operation, and it returns to the corresponding output pixel. So bitwise AND does that, and you will get such image, the output image. So this image 1, this image 2, and this is image 3. What it does is it performs the AND operation for all the images. So what it does is, so it performs the AND operation for this, since I'm assuming black as 0 and white as 1. So this portion is black, so this portion is 0. This portion is black plus white. Let's say for this portion it's 1 and this portion is 0. So 1 into 0 is 0, so it's dark here, and 0 into 0 is also 0, so it's dark here. So entire this channel is 0, and corresponding this is high and this is high. So this part is printed high, that is white, and the remaining part, which is not the same, 0 and 1, so it's not same. So it will be printed low, that is black. So this is how you get, this is how you perform bitwise AND on the image, and this is the output for these two images. Now let's see the bitwise OR. So this is the bitwise OR. It works in the same way that so bitwise OR, it's high here, and the remaining portion is 0. So it prints this portion in the output will be high, so it's high. And here the OR operation over these two parts of the image, since this is already high, it will not bother of this part, and it will directly print it as high, and hence we have this particular image as the output. And this is a simple one. Now it's the XOR operation. Now performing the XOR operation on the image. So as I told earlier, if both the values are high, if both the values are same, it will give a low. If both the values are different, it will give a high. Or if there are even number of high resolutions, then it will give low. If there are odd number, it will give high. So let's see each section. So for this section, this is low. One second, I printed the wrong code. Okay. So yeah. So yeah. Okay. Let me explain it. So if both the parts are same, then it will print a low, and if both the parts are different, it will print a high. Uh, so since this part is same for both the sections, it will print a low, that is black. And since these two parts are different, it will print a high for this resolution, and it's high here. And these two are same, so it is low there. And coming to this half of the image, we see that this and this point, this section are the same, so it will print black, and these sections are different, so it will print a white. So this is how XOR operation works. And now we'll see the NOT operation. NOT operation is straightforward and direct. So okay. So I'm passing on this accepts only one argument, that is image 2. So I'm finding the NOT operation of only image 2. So we can see that for image 2, black is white and white is black. So it is performing the NOT operation, and this is how we get this is how we perform the Bitwise NOT for this image. So yeah, that's all for this session. If you guys have any doubts, you can ask me.